Good afternoon, all of you. I, Dr. Priyanka Singh, working as an assistant professor in Applied Science Department, IIMT College of Engineering, Greater Noida. Today, I am going to present a lecture on the topic, the development of calculus and its future scope. In this lecture, I discuss some of the topics which are as follows. Now, first of all, I discuss introduction of calculus, which is as follows. In mathematics, geometry is defined the study of shape. Algebra is defined the study of generalizations of arithmetic operations and their application to solving equations. Calculus is defined the mathematical study of continuous change. Calculus is one of the most important branches of mathematics that deals with the study of the rate of change that are not constant was developed by Newton and Leibniz. Today, calculus was widespread uses in science, engineering, and economics and can solve many problems that algebra alone cannot. Calculus is a major part of modern mathematics equation. A course in calculus is a gateway to other, more advanced courses in mathematics devoted to the study of functions and limits, broadly called mathematical analysis. The calculus of infinitesimals is another name for calculus, which is also referred to as infinitesimal calculus. In its most basic definition, classical calculus is the study of continuous change in the behavior of mathematical function. For example, velocity is equal to the change in distance with respect to time, and distances is equal to the change in velocity with respect to time. Calculus focus on some important topics covered in math such as differentiation, integration, limits, functions, and so on. Next, I discuss origin of calculus. The word calculus comes from the Greek name for pebbles, meaning small stone used for counting. Because such pebbles were used for counting out distances, telling words, and doing abacus arithmetic, the word come to mean a method of computation. Calculus has also been borrowed into English as a medical term that refers to masses of hard matter in the body, such as kidney stones. Pebbles were used for counting and doing simple algebra, a method of computation or calculation in a spatial notation like logic or symbolic logic. More generally, calculus, plural calculi, refer to any method or system of calculation guided by the symbolic manipulation of expression. Some examples of other well-known calculi are propositional calculus, calculus of variations, lambda calculus, and process calculus. Next, I discuss definition of calculus. Calculus is a field of a mathematics that was developed by Newton and Leibniz and is concerned with the study of change at a certain rate. Generally, calculus maths is employed in mathematical models in order to find the best possible results. It assists us in comprehending the changes that occur between the values that are linked together by a function. Calculus maths is primarily concerned with a few important topics such as differentiation, integration, limits, functions, and so on. Calculus maths is requirement for many other maths courses. Calculus in mathematics is generally used in mathematical models to obtain optimal solutions and thus helps in understanding the changes between the values related by a function. Classification of calculus. Calculus is divided into two branches, is a differential calculus and integral calculus. It is denoted by is a symbol. Differentiation is dy by dx. Y is differentiating with respect to x, and integration, y is integrating with respect to x. This one is implications of implications. Differentiation is changing to integration and integration is changing to differentiation. These two are like opposite simplex of each other. That is because if you take the derivative of a function and that take the integral of it, you return to where you started. The two major concepts that calculus is based on are derivatives and integrals. The derivative of a function is the measure of the rate of change of a function and slopes of curve, while integral is the measure of the area under the curve of the function. The derivative gives the explanation of the function at a specific point, whereas the integral accumulates the discrete values of a function over a range of values. These two branches are related to each other by the fundamental theorem of calculus. Both branches make use of the fundamental notions of convergence of infinite sequences and infinite series to well-defined limits. Next, I discuss development of calculus. First, I define earliest calculus type concepts. Most of the mathematics come together in the mid to late 17th century. Certain calculus concepts go way back. Abacus and Archimedes applied a primitive version of the limit concept in their method of exhaustion. They found some areas and volume by subdividing region. Example, circular disc, into smaller pieces for which they knew the area, regular polygons, and let the number of pieces grow. Polygons with more sides. This is very much the same basic idea that we have for a definite integral. Next, exhaustion example is the area of parabola being approximated by exhaustion method. Next, rectangles for approximations. Here I consider example of exhaustion method. Here I am taking a function y is equal to f of x is equal to x square plus 1. If I putting x is equal to 1, then we have to finding y is equal to 2. So here I draw point 1 to 2. Next, again I putting value x is equal to 2, then we have to finding 5. So here I drawing is a 2 and 5. Similarly, I putting 3, then we have to finding 10. So 3 and 10, I draw 3 to 10. Again, we have to putting 4, is a we have to finding 17. Again, we have to putting is a 5, then we have to finding 26. Next, I define is a rectangular form, and next is a points 2, 5, 10, 17, 26. I draw a curve. Then we have to finding a rectangular area of the curve. Next, Greek work with the conics was particularly important in laying some foundation for calculus. Numerous other advances in mathematics, including establishing our modern numeration systems, developing algebra, and further development of geometry, all help provide the foundations necessary for developing calculus. Establishing calculus concept and techniques. Analytic geometry and related concepts were developed in the early 17th century by Fermat and Descartes. Fermat is found maxima and minima of specific functions through of as curves, found tangent to curves, found area under curves by summing area of rectangles. Descartes found tangent lines to curve, but used a slightly different method than Fermat. These are certainly calculus techniques and concepts, but as yet, they were for special cases and is not yet a fundamental theorem of calculus. Kepler found area and volumes using methods similar to Archimedes. Torricelli calculated volumes of indefinitely long cylinder. Cavalieri method of indivisibles area are made of indefinite number of lines, like threads in a cloth. Volume are made of indefinite number of areas. Pascal worked with a differential triangle influenced by Leibniz. Wallis found area under functions with fractional exponents. Gregory worked on calculus at about the same time as Newton, but did not publish his method. First to publish a proof that methods of tangents and the method of quadrature were inverses. Fundamental theorem of calculus transformed integrals by change of variables. Similar ideas as Newton arrived at independently. Near the same time, by 1668, he was familiar with series expansions of sine, cos, tan, and had developed some derivatives and antiderivatives formulas. Barrow is the first Lucasian Chair of Mathematics and Natural Philosophy at Cambridge in 1663. His student Newton was the second chair in 1669. Geometry stated the first and second fundamental theorem of calculus. Beginning of integral calculus, the modern notation of an integral in which the differential dx is placed on the right-hand side of the expansion can be interpreted as the increasingly small of infinitesimal base of each rectangle. For this reason, before calculus was completed, the logic behind integration was attacked for being non-rigorous. Integration x to the power 3 dx. Beginning of differential calculus. While integral calculus can be understood by taking an integral to simply mean the area under a curve, differential calculus pivots on the idea of the derivative. A derivative can most easily be understood as the slope of the tangent line to a curve at a specific point. The fundamental theorem of calculus. The fundamental theorem of calculus is defined. The function f of x is continuous. Then you can calculate f of x by the equation on the right. So it is defined by, it is formulated by integration of a to b f of x dx is equal to f of b minus f of a. This graph is defined is a function is continuous. Next, the founder of calculus, Newton. Newton is one of the giants in mathematics and science. His work on optics and gravitational make him one of the top physicists of all times. He is also considered one of the greatest mathematicians of all time, first to develop calculus. Leibniz created his calculus is basically the modern version. He taught the most influential developers of calculus over the next century, including Jacob and Johann Bernoulli. One thing of significance about the work of Newton and Leibniz is the fact that every discovered that differentiation and integration are reciprocal operations. Therefore, if we integrate a function, we can differentiate its result to get back the original function. Cauchy created the following definition of a limit when the successive values of a variable approach certain fixed value infinitely if the difference between it and this fixed value can be arbitrarily small, then the fixed value is called its limit. This definition allowed for infinitesimal quantities to be considered as simply quantities with a limit of zero. Hence, the objection to the logic behind calculus concerning infinitesimal quantities is successfully refuted. Next, Weierstrass, the father of modern analysis. Weierstrass improved on Cauchy's definition of a limit with his epsilon del limit definition. Limit extending to a f of x is equal to L if and only for every epsilon greater 0 there exists del greater 0 for all x belong to D. X mod of x minus a lies between 0 to del, then this one is a implies mod of f of x minus L is less than epsilon. Weierstrass limit continued. Weierstrass' definition of a limit solved any remaining problems concerning the uncertainty of infinitesimal quantities. It does not matter how L is approached so long that it is approached such that the final difference is smaller than epsilon. With this definition of a limit, calculus foundation was able to be successfully rebuilt. Reconstruction of the integral. With the new limit definition, the integral become a limit with a rigorous and logical base. No longer depend on the infinitesimal quantity, which was objected to. Uncertainty in integration disappeared. Here, A is the limit, which can be understood as the limit of the area of the sum of n rectangles. So here, this graph is defined, function is continuous at a point A to B. And A is defined as the area covered by this function. So this is defined by area is equal to a to b f of x dx. Reconstruction of the derivative. Next, we change this fundamental theorem of calculus in differential form. So f dash of x is equal to dy by dx is equal to limit del x tending to 0, f of x plus del x minus f of x upon del x. With the Weierstrass definition of a limit, derivative are no longer dependent on the ratio of infinitesimal quantities, but can be regarded as a limit. This is due to a tangent being regarded as the limit of the secant, such that the slope of the tangent line is the limit of the slope of the secant. Therefore, the derivative becomes a limit itself. The traditional Leibniz notation for differentials dy by dx is still used, but now we use limits to define the differential rather than simply letting differentials by infinitesimal. Lebesgue. With calculus, while many functions were easily able to be integrated, functions such as the Dirichlet function were not so easily integrable. In order to properly determine if a function was integrable, the great mathematician Henry Lebesgue devised the Lebesgue integral, which extended the integral to a larger class of functions. F of x is equal to 1, 0. If x is rational, if x is irrational. The approximation of calculus in the application of calculus in everyday life. In engineering, real life applications of calculus is incredibly prevalent in the field of engineering. Let's discuss a few of its applications below. First, structural engineering. One of the most critical applications of calculus in real life is in structural engineering. Calculus is used to calculate heat loss in buildings, forces in complex structural configurations, and structural analysis. In seismic design requirements, architects use calculus to determine the ever important quantities of materials required for constructing support systems that can withstand stress over long periods of time. Even notable moments, such as the Eiffel Tower, were constructed using calculus to predict the impact of wind resistance. Computer science engineering, computer graphics, image processing. And here will also be needed analytic geometry and linear algebra. In this sector, students need to study some differential geometry which has multivariate calculus. Here, even for every basic things like Fourier transform and wavelets, for example, these are two very fundamental tools for pupil working with image. Optimization, nonlinear mostly, where multivariate calculus is the fundamental language used to develop everything. But even linear optimization benefits from calculus. The derivative of the objective function is absolutely important. Probability statistics, this cannot be seriously studied without multivariate calculus. Machine learning, which makes heavy use of statistics and consequently multivariate calculus. Robotics, where a programmer will need to model physical movements of a robot. So he will need to know partial derivatives and gradients. Scientific computing, computer algebra systems derivatives directly, either symbolically or numerically, are the most blunted examples here, but in addition, any software that simulates a physical system that is based on continuous differential equation. Example, computational fluid dynamics, necessarily computing derivatives and integrals. Civil engineering, when designing bridge, civil engineers need to consider three structural elements: beam, tension, and compression members. Using calculus, we can determine the amount of force acting on the beam, including the weight of pedestrians, weight of vehicles, and the amount of traffic anticipated on that bridge. Based on these factors, the material size and capacity can be computed. Electrical engineering, integral and differential calculus are crucial for calculating voltage or current through a capacitor. Integral calculus is also a main consideration in calculating the exact length of a power cable necessary for connecting substations that are miles apart from each other. Mechanical engineering is yet another great example. The pump used for filling an overhead tank, gardening tools, cars, motorcycles, robots, and many household appliances are designed using the principles of calculus. Spaceflight engineering, before launching a rocket or exploratory probe, engineers must use calculus to figure out the gravitational pulls of the sun and moon in order to know how to launch a probe or hit the velocity needed to orbit the earth. Medicine. In medicine, calculus can also be applied in medicine. Applications of calculus in medical science include bacterial growth. Biologists use differential calculus to compute the exact bacterial growth rate in a culture by varying environmental factors such as temperature and food source. Patient diagnosis. Calculus is crucial in medical tests used for measuring cardiac output, blood flow, and tumor growth. This data is needed to properly assess a patient's health condition. Epidemiology. Epidemiologists who conduct research on infective diseases use calculus to discover the spread rate and area where an infection will likely occur. Calculus can also help create a containment plan and investigate the source of an infection. Cancer. Calculus is used to determine the growth or shrinkage and number of cells of a cancerous tumor using an exponential function. Oncologists analyze the progression or regression of a disease. Surgical control of red blood cells. The blood in the human body is made up of red blood cells. While undergoing surgery, a patient's blood volume has to be mentioned by injecting a saline solution that mixes quickly with the blood and dilates as time passes. Calculus is used for computing the volume of red blood cells. So the proper amount of saline solution can be given to the patient during surgery. Cardiology. Cardiologists use differential calculus to understand the blood flow dynamics needed for building an artificial aorta model in order to make sure it is placed correctly during transplant. Pharmacology, understanding drug sensitivity is crucial in finding the proper doses for maximum output of drug integration. The side effects of a drug uh, brought about by factors like body temperature change can be computed through integral calculus. Pharmacologists can make a kidney a changing function in the calculus based Cockcroft-Gault equation and determine the creatinine levels in the blood to access the kidney's functionality. Using these results, the doses of drugs for treatment can be finalized. Neurology. Neurology is the study of the human nervous system, which is very complex network of neurons that pass the brain's signals to the entire body and control all physical activities. The system consists of the central nervous system, the brain, and the spinal cord. Integral calculus is used to compute the voltage of a neuron at a certain point. In contrast, differential calculus is used for calculating the change of voltage in a neuron with respect to time. Entomology. Entomology is the study of insects. An entomologist conducts research, classifies insects based on species, and finds safe solutions to control insects infestations in indoor and outdoor environments. Calculus is used for modeling and generating insect proficiency through partial derivatives. Business. Modern business also benefits from the application of calculus. Some of its uses included credit card payments. Calculus is used for setting payments structures and the minimum due amount by the credit card company by considering variables such as interest rates and fluctuating balance. Economics, the price elasticity of supply and demand is determined using calculus. Economists use variables such as the supply demand curve to find the exact measure of elasticity at a particular point according to change in price. Music. You may be surprised to know that the use of calculus is not restricted to engineering or medical science, but can also be applied to music. Some applications include harmonics. An oscillation created by a damped harmonic is not infinite as friction and air resistance will dissipate the energy. Calculus is used to anticipate these motions to make the proper adjustments and provide the best musical experience to the listeners. Acoustics. Resonance and forced oscillation can be computed using calculus. A resistance varies at different frequencies and resonates throughout an enclosed space whenever a musical instrument is played. Through calculus, we can make improvements on acoustics and improve the listener's experience. Research analytics. The application of calculus in research and development has paved the way the manufacturing, data management, gaming, and other service industries to grow exponentially. These applications include variables in manufacturing. Research analytics use calculus while observing different processes. Based on collected data, companies can optimize their output, productivity, and efficiency, which improves the industry's equality and revenue. Evaluate survey data. Statisticians make use of survey data to find a range of answers for different questions. Using calculus allow them to make accurate predictions, which helps their decision-making process. Computing birth and death rates. Ecologists use calculus to make dynamic population models that showcase growth without any environmental constraints. Through calculus accurate predictions on population change can be made, taking birth and death rates into account. Simulation for video games, graphic designers use calculus to understand 3D models created through changing conditions based on the result derived from calculus. Video games and animated movies are made with a real world perspectives. Now, now I discuss use of calculus in catenary equation. So first is what is a catenary? If a heavy uniform string or chain hangs freely between 2 points and not in the same vertical line, then the curve in which it hangs under the action of gravity is called a catenary. Here in this diagram, we have to finding intrinsic equation of common catenary. In this diagram, ACB be the uniform string or chain suspended between 2 points A and B, and C being is the lowest point. Next, T naught is defined as a tangent at a point C, and next T is a tangent on the curve AC, and this one is a creating angle is a psi on OX axis. Next is a length of curve AC is equal to S. P is a point in the curve AC, and this CP curve is a length is S, and W is the weight of this string. This angle, this tangent is creating the angle, then is a horizontal line. Horizontal line is defined is a T cos psi, and is divided into two axes is a T cos psi, and vertical axis is defined as T sin psi. So OX and C is a T naught is a parallel, then T naught is equivalent to of T cos psi, and is a vertical is a WS is the total weight of this string. So T sin psi is equal to WS. Next, equation 1 is defined T cos psi is equal to T naught, T sin psi is equal to WS. Next, are dividing equation 2 by equation 1. So T is cancelled, sin psi upon cos psi is equal to tan psi, and WS upon T naught. And T naught is equal to WC, because C is a set C is a lower point of string, and total weight is a W, then is a weight of a length C. So total T naught is equal to WC. So here in equation 3, we have to putting T naught is equal to WC. So WW cancel. We have to finding S is equal to C. And after cross multiplication, we have to finding intrinsic equation of the catenary. S is equal to S is equal to C tan psi. Now we have to finding the Cartesian equation of the common catenary. The intrinsic equation of the catenary is defined as S is equal to T sin psi. We know that tan psi is a tangent. So this one is defined as a dy by dx. So differentiating both sides with respect to x, so we have to finding ds upon dx is equal to c d square y upon dx square. Next, ds upon dx value I put it is a under root 1 plus dy by dx whole square is equal to c d square y by dx square. Next, I putting dy by dx is equal to p. So this equation 2 is changed is under root 1 plus p square is equal to c dp by dx. Next, after cross multiplication, we have to finding dx is equal to c under root 1 plus p square dp. Next, I integrating on both sides, then we have to finding x is equal to c sine hyperbolic inverse p plus constant a. A is constant of integration. Now I finding is a constant value of a. So choose the vertical line, throw the lowest point c of the catenary as y-axis, then at c, x is equal to a. So dy by dx is equal to 0 as a tangent at c parallel to x-axis. Now putting p is equal to 0. So 0 is equal to c sine hyperbolic inverse of 0 is equal to plus a. So a is equal to we have to finding 0. So x is equal to we have to finding c sine hyperbolic inverse p. Next, c I transform on the left hand side. So x upon c and sine hyperbolic I transform on the left hand side. So p is equal to sine hyperbolic x upon c. Next, I putting value of p is a dy by dx. So is equal to sine hyperbolic x upon c. Dy is equal to sine hyperbolic x upon c dx. Now I integrating on both sides. So y is equal to cos hyperbolic x upon c and x upon c is a integration is a c sine cos hyperbolic x upon c plus constant b. Now I finding is its constant value of b. Now choose the origin O at depth C on y-axis and let the horizontal line through O be taken as x-axis, then the coordinates of the lowest point C, B 0, C. At C, from equation 4, we get C is equal to C cos hyperbolic 0 plus B. C is equal to cos hyperbolic 0 is equal to 1, so C plus B, so C is cancelled, B is equal to 0. So we have to finding y is equal to C cos hyperbolic x upon C. This is the required Cartesian equation of the common catenary. Now, after study of calculus, I conclude that with calculus, we have the ability to find the effects of changing conditions on a system by studying this. We can learn how to control a system to make it do and control systems. Calculus gives us extraordinary power over the material world. Derivatives are constantly used in everyday life to help how much something is changing. They are used to engineering, medical and business and so on. The fundamental theorem of calculus enables us to evaluate definite integrals that empowers us to find the area between a curve and x-axis. Lastly, I discuss future scope. More specifically, calculus may be extended as follows. It is possible to perform various image graphics, image processing, and robotics tasks by multivariate calculus by converting theory of calculus to new algorithms. To extend the theory of calculus in robotics modeling, planning, and execution tasks by a mathematical modeling. To extend the theory of calculus to venture into the future of machine learning, data science, artificial intelligence by mathematical modeling. To extend the theory of calculus into the future astronomy problems, example, rocket launching by mathematical modeling. It is possible to perform various business problems in future, example, credit card payments, economics aids, by converting theory of calculus to new algorithms. To extend the theory of calculus in biomedical sciences to simulate complex biological processes of human health and diseases with high fidelity by a well-designed mathematical model. Example, in silico modeling. References. Thank you.